Okay, so we left off taking a look at solution curves to y prime equals t minus y squared, and now we'll proceed from there. So I wanted to talk a little bit about some special cases for some direction fields. The first case is y prime equals f of t, and so if y prime is a function of t alone, by the way, this is the case that you typically look at in calculus. So for example, you might say, well, if y prime is equal to t, right, then y of t is equal to 1/2 t squared. It's just the antiderivative. So this is a fairly simple differential equation to solve, but we still want to think about what the direction field would look like. So in that case, the solution depends only on t and not on y. And so notice that that means that the function or your solution could be shifted up and down and wouldn't change your direction field at all. You wouldn't change the slopes. And so that's why we can add a c right to the end of our function. And so I guess we could take a look at a quick example. For example, y prime equals t squared. Let's take a look at in the plotter. So if we just say y prime is equal to t squared. Oh, let's do well, t squared is okay. Graph the direction field. Okay, so you see here again that these functions are, or the slope field, the slope of these lines are the same, no matter what the y's are. So along any vertical line, all your slopes are the same. Good. And so you might even do something like, let's say cosine of t. Right, so, and then in this case, this is easier to see. All your solutions are just shifts of each other. Good. And so in the other case, the other special case would be where y prime depends only on y alone. Now this case is more difficult to solve. We're going to actually get a formula or get a way of solving this in a little bit in the next chapter. But graphically, we see is the slopes depend only on y, not on t. So what does that mean? That means no matter what time, if you're going along a curve where y is fixed and t is ranging, that means you're along a horizontal line. And so along any horizontal line in the graph, all the local slopes will be the same. Right? So the slopes along any horizontal line are the same. So let's do an example. Y prime equals y times 4 minus y. By the way, before we go to the plot, if we look at some of the isoclines, for example the 0 isocline, we end up with y equals 0 or y equals 4. These are actually two special isoclines because those are also solutions to the differential equation. On the other hand, if y prime was like equal to 1, that would be a whole different ball game, right? But in this case, if y prime is equal to 0, those are called y equals 0 and y equals 4 are called equilibrium solutions. And so we're going to see that in just a second on this online plotter. And so when you go to type this out, we'll have y times 4 minus y. Okay, graph the direction field. Good. And so now, do you see the two solutions? The y prime. So there's an equilibrium solution at 4 and an equilibrium solution at 0, like exactly what we were saying. And along any horizontal line, all the solutions are the same. Good. All right. So those are two special cases. How about this one? So suppose we go backwards. Suppose I give you the direction field. Could we come up with a differential equation of the form y prime equals ay plus b, whose direction field looks like this? Well, we see that y equals 1 is the only is going to be an equilibrium solution. That's where the derivative is 0. right? So if I write 0 in here, then y should be equal to 1, right? That's my equilibrium. And so what we were saying before when we were solving this differential equation, remember the general solution was y equals c e to the at minus b over a. Okay, well, maybe I'm talking too much. Maybe we should continue on here. Two requirements for this. One is that a should be less than 0 so that our solution converges. And then the other one is that the minus b over a is equal to 1, right? Because our solution is c e to the minus at minus b over a. Good. So we need a to be less than 0 so that all of our solutions are converging to the equilibrium. So the a has to be negative. And secondly, minus b over a must be equal to 1 because that's what everything is converging to. So for example, y prime equals minus y plus 1. Remember what the solution to that is? That's going to be c e to the minus t plus 1. Good. How about this one? This is very similar. In this case though, what do we see? We see one equilibrium solution at -1, we'll say, and then every other solution is diverging from that. So if we're looking at something of the form y prime equals ay plus b, in this case a must be positive and minus b over a must be equal to -1. Good. So what would a solution to that look like? Oops, I guess I didn't write it down. Y prime equals y plus 1, would that work? Y prime equals y plus 1? Give it a try. In fact, I guess we could just try it. How about if we see, if over here we say y plus 1? Do you think it'll, oh hey, that looks familiar. Good. So that's our differential equation for that one. Okay, now what's next? Here's a direction field. Can we choose a differential equation that matches the direction field? Well, first off, you want to identify the equilibrium solutions if there are any. Actually, this is looking very familiar to us, isn't it? So let's see, we have one at 0 and one at 3. So which of these differential equations has two equilibrium? One at 0 and one at 3. This one has one at 3 but not one at 0, so 1 is out. 4 is out obviously because it doesn't have the right equilibrium. 2 has the equilibrium at 0 and -3, so that's out. And so number 3 is the only one that will work. And so you'll be doing some matching problems in the textbook, so that'll kind of help along. So if one of these had a negative sign, like if this one had been minus y times y minus 3, then this could have also been a possibility. And the way to tell the difference is to pick a number like either between 0 and 3 or greater than 3, and then plug it into the differential equations to see if your slopes are positive or negative. So for example, if I plug in y equals 2 into this differential equation, I get a 5 times 2 is 10, right? So that's going to be a positive slope. Well, if I had a negative sign in front, it would be a negative slope. Here, if I plugged in a 2, that would be 3 minus 2 is 1 times 2. So this is a positive 2 slope. And so you can see here that this looks like a positive 2 slope is probably a good guess. Very good. So I will let you think about those other graphing or the matching problems in the 1.1 homework. Good. Just a quick note about some modeling for the sphere. It's we know that the volume of a sphere is 4/3 pi r cubed, and the surface area is 4 pi r squared. And so if the rate of change is proportional to the surface area, then we know that we could write a differential equation of this form. But the idea is you want to write v prime in terms of v only. So see if you can use these two equations and manipulate them so that you can write your derivative all in terms of v. Okay, that's my only hint. Send me an email if you have any questions about section 1.1 or anything earlier. Otherwise, I will see you later.